we are at a very important section of rotational mechanics now. We are coming towards the end. So last time we discussed about angular momentum and about general rigid body motion. Let's take a quick recap of the two concepts that we had learned over there. So general rigid body motion, we saw, is a combination of translation and rotation occurring simultaneously. But the rotation always occurs about the center of mass axis. So if a rigid body is moving such that the center of mass has a linear velocity Vcm, the body has angular velocity omega about its center of mass. So center of mass has a linear velocity of Vcm, while simultaneously the body rotates about its with angular velocity. So remember, angular velocity is an axial vector. So then the linear momentum the body P will be total mass into velocity of center of mass, and its angular momentum about the center of mass will be given by moment of inertia about the center of mass axis into angular velocity. But we saw another thing, that we can also define the angular momentum about another general point, which may even lie outside the body, like the origin I'm drawing over here. So at the given instant of time, the position vector of the center of mass with respect to this origin point is RCM. We can also write the angular momentum about the point P about a general sort of point, which you can arbitrarily select O. So that angular momentum about O is given by the formula RCM cross MVCM plus the angular momentum about the center of mass, which is this. So these were the important momentum related formulae, both translational or linear momentum and angular momentum or rotational momentum. Angular momentum can also be called rotational momentum, just like linear momentum can also be called translational momentum. Okay. Now today we will also discuss about the total kinetic energy of such a body. So we are coming to that. You can just make a quick note of the important points here. Okay, so these are the important things here: the linear momentum, the angular momentum about the center of mass, and the angular momentum about a general point. Now, next in this list, let's come to concept of the kinetic energy of such a body. So the total kinetic energy here will be the sum of kinetic energy of translation energy due to rotation. So this is called the translational kinetic energy, and this is called the rotational kinetic energy. This is the total kinetic energy. So that is given by half mbcm square plus half of moment of inertia about the center of mass axis into omega square. So this becomes the formula for the total kinetic energy of a body which is moving in the combination of rotational and translation, as we've seen above. So this is the next important property of its motion, the total kinetic energy. Okay, so let's look at an example problem based on this now. So we have a situation like this, that with respect to a standard XYZ coordinate system, we have a rod that is moving in such a way that at a certain given instant of time, this is a thin uniform rod, mass m, length l. At some given instant of time t equal to t, its center of mass is located at a certain position and is moving with a certain velocity, while it's also rotating with an angular velocity omega. So at a certain instant of time, its center of mass is located the point and is moving at a velocity, so let's say in the xy plane, in meters per second, while the rod is rotating, as you can see, clockwise about an axis parallel to, or we'll just say an axis perpendicular to the xy plane. Through its center of mass at an angular speed equal to 2 radians per second. Given that mass of the rod is 5 kilograms and its length is equal to 2 meters. Now we want to calculate its linear momentum, its angular momentum about its own center of mass axis, its angular momentum about the origin, to find out its total kinetic energy, and we want to find out its translational kinetic energy and rotational kinetic energy separate. So just try out this question. I'll explain all the parts in a minute or two. So I'll just start out by listing all the formulae that you will have to use. In
Sir,
linear
can
momentum.
you show that upper part?
Okay. Okay, complete writing down this part, then we'll come back to the question.
Sir, you can take down. Sir, done. You can take down.
capable, at least the first couple of things were very simple to solve here. You should have been able to give the answer by now. Anyhow, so let's look at it. So the linear momentum is just defined as total mass into velocity of the center of mass. So total mass was 5 kilograms and velocity of center of mass is given to us. It is 3 I cap plus 4 j cap in meters per second. So the linear momentum you can see is 15 I cap plus 20 j cap in Newton second or kilogram meters per second. You can see its magnitude. So it will be 25 Newton second. Yes. Then the angular momentum about the center of mass is going to be moment of inertia into angular velocity. Now you can see that the rod is rotating clockwise. It's shown to you. Okay, and this is our xy plane. So you can see for this omega vector, the n cap is minus k cap. It's into the plane. Okay. So moment of inertia about the center of mass axis is ml square by 12, and the angular velocity with a vector sign will become minus omega k cap. So the angular momentum about the center of mass is ml square omega by 12. Unit vector is minus k cap. So it's 5 into the length was 2 meters, I think, right? Yeah, 2 meters, and the angular speed is 2 radians per second. So 5 into 2 square into 2 by 12. That's 10 by 3, right? That is the unit of angular momentum. Unit of moment of inertia, kg meter square, into unit of angular velocity, which is in radians per second. So it becomes kg meter square per second. That is angular momentum about the center of mass. Now the third one is slightly more tricky one. The angular momentum with respect to the origin is r cross linear momentum of the center of mass plus ICM into omega. So note down these two parts. Hope you have understood this. And now try to figure this out, this third part, from the data given as well as from the method I've shown you below. Try to figure this out. Should not be too difficult. Please send me the answers. Okay, after working out the third part. Okay, so still nobody has sent me the proper answer for the vector value of this angular momentum. So let me work it out. So you can see the position of the center of mass with respect to our origin, okay, was given to us. The center of mass, its coordinates are given above. See, its coordinates were 2, 3, 5. And its velocity was also given to us separately. So this quantity here, it becomes 2i cap plus 3j cap plus 5k cap, cross product with 5 kg multiplied by 3i cap plus 4j cap. That is this term. And ICM omega we had already seen earlier. It is 10 by 3 minus k cap. So now this cross product we can work out. So this is my RCM cross VCM. That is minus 20 I cap plus 15 J cap.
How omega acted minus k cap can you explain?
Omega is clockwise. So it's going into the plane. Into the plane is the Z axis, negative Z axis. So X and Y are like this. Is it clear?
Yes.
So this will become 5 kg multiplied with plus. So you can see it is minus 100 I cap plus 75 J cap minus of 5 plus 10 by 3. That's 25 by 3 K cap. This is the angular momentum about the point. So it's this sort of full calculation that we have to do in this kind of a situation. Now let's turn our attention to the kinetic energies. So last part of the question. So the translational kinetic energy is this much. The rotational kinetic energy is this much. And the total kinetic energy is just the sum of the translational kinetic energy plus the rotational kinetic energy. So this is a scalar calculation. It's not as difficult as the angular momentum one, which is involving a vector cross product. Okay, so coming to the last part now, we can see that so VCM is mod of 3 I cap plus 4 J cap. So that's 5 meters per second. Kinetic energy of translation is 125 by 2 or 62.5 joules. This is a translational kinetic energy. Whereas the rotational kinetic energy, omega was 2 radians per second, and moment of inertia about center of mass so that is 5 by 3 kg meter square. So the rotational kinetic energy comes out to be 10 by 3 or 3.33 joules. The total kinetic energy is the sum of translational kinetic energy plus rotational kinetic energy. Okay, now let's move on to the next aspect about general rigid body motion. So we saw impulse momentum theorem. For the general rigid body motion. So we saw that the net linear impulse is equal to the change in linear momentum. Net linear impulse equals to the change in linear momentum. Whereas net angular impulse, so this is net angular impulse, but we always take about center of mass, because there's no fixed in general rigid body motion. So that is equal to the change in angular momentum about center of mass. So these together represent the impulse momentum theorem. That angular impulse equals to change in angular momentum. Linear impulse equals to change in linear momentum. Okay. So for example, we have seen questions based on this in the last lecture also, but let's look at a different type of question based on this now. So we have, let's say,
that is same theorem, no? You have taught now.
yes, this theorem we had seen applications of in the last lecture also, including those collision type of problems we saw, right?
Yes.
But we'll see a slightly different type of problem based on this today. So there is this.
We don't have to write that, no?
Yeah, you need not write it, or it's just one formula, so you can write it down under the heading. The more important thing is the application example I'm showing below, right? So this is a smooth horizontal surface. And this is a solid sphere which has mass m and radius rx. Okay. Now what happens is that the solid sphere is initially at rest, but we hit it with a sharp impulse. Like, imagine when you hit a billiards ball or a pool table ball with the cue of the pool table, that stick. But instead of hitting it at the center, you are hitting it a little bit above the center. So you are hitting it with a line of action, which is like this. So a sharp impulse J is applied like this on it, which is, I'll explain how it is, okay, in the question. So the solid sphere, let's take some values. Its mass is, let's say 500 grams, so 0.5 kg, and its radius is, let's say, 20 centimeters, so 0.2 meters. Okay. So this solid sphere is initially at rest. Okay, on the smooth surface. Now, at time t equal to 0, a sharp horizontal impulse, the type you would get from an impact, that kind of impulse of magnitude, let's say, let's say 0.1 Newton second is applied on it, such that the line of action, that is a line along which the impulse is acting, for this impulse is d equal to r by 2 vertically above its center of mass. Okay, so the center of mass of the sphere is here. Then this line, this dotted line along which this horizontal impulse is acting, is exactly vertically above the center of mass at a distance of r/2. So we want to find the velocity of the center of mass, the angular velocity about the center of mass, and the kinetic energy for the motion of the sphere after t equal to 0. So just try to apply the above impulse momentum theorems to this question now. We will discuss about this.
So this is type of rolling motion.
Not exactly going to be rolling in this particular case, but in a special case of this type of motion where there's a relationship between the VCM and omega, that is called the rolling. This is more like a general rigid body motion where there is combination of translation as well as rotation. Rolling involves a bit more of a specific condition. We will come to that. Okay. Okay, so let's understand this question in detail. So what's happening here is that
Can you take up one?
I'm explaining the question now. So let me finish that first. So before that impulse acted on it, the net force and the net torque was zero. So the weight and normal reaction are balancing each other. So this is a system which is at rest and at equilibrium. And then we apply an impulse on it like this. A sharp impulse is applied horizontally like this, acting through this horizontal line, such that that line is at a distance of d equal to r by 2 above the center of mass. Okay. So what will happen is when we talk about net impulse, that is going to be j over here, and net impulse is equal to change in linear momentum. So what was happening is before the impulse acted, it was at rest. So VCM was also zero. Omega about center of mass was also zero. But after application of the impulse, this will now, as you can logically understand, it will start moving such that the center of mass is moving horizontally and about the center of mass. So after VCM is equal to some value which you want to calculate, and omega is going to be some non-zero value which you want to calculate. So when we apply this over here, this equation, this becomes that J becomes MVCM. Or if we write a scalar version of this equation, J is equal to MVCM. So this equation will tell us the linear velocity of the center of mass. Okay. So as a result of this impulse, the center of mass will start moving horizontally with a velocity which is according to the values given. So J was 0.1 Newton second and the mass was 0.5 kg. So in SI units. So velocity of the center of mass will become 1 by 5 or 0.2 meters per second horizontal. Okay. Now the second thing, so this is the linear impulse.
So you can use that formula, na? Angular impulse equal to
Yeah.
linear impulse into momentum.
Now the next is we'll use the angular impulse momentum theorem. And that is that the net angular impulse is equal to change in angular momentum. So this is equal to change in angular momentum. Now here the net torque is R cross F that is acting through this. So the net angular impulse is going to be R cross J. Okay, so this is the important thing. This is the net angular impulse about the center of mass. So now you can see that the moment arm for this J, the point where it's acting is actually this. So this is your R vector. When we take the cross product, it actually becomes this perpendicular distance into this. Okay, so this angular impulse, its magnitude will be linear impulse into momentum. So the magnitude of angular impulse will be JD, which in this case is JR by 2. Okay. And you can see that its direction will be clockwise because R is a vector like this and J is a vector like this. So R cross J will be clockwise. Anyway, you can understand that this will give us a clockwise. Okay, so this will be, so the angular impulse will be j into r by 2 and its sense will be clockwise. So now we apply the theorem that angular impulse equals to change in angular momentum. So jr by 2 will be equal to I omega because the initial angular momentum was 0. So delta L is the final angular momentum minus the initial angular momentum. The initial was 0 and the final is so a change in angular momentum has this magnitude and it's clockwise. So jr by 2 will now, for a solid sphere, you should remember that 2 by 5 mr square is the value of moment of inertia. So from this we'll get the value of omega as 5 by 4 j upon mr. We calculate its magnitude also in radians per second. But parametrically it's like this and it will be a clockwise. Okay. So I'll just minimize this a little now. You can go back and any information about the cone again, you can do that, and then we'll come back to the application of the two theorems: linear impulse momentum theorem and angular impulse momentum theorem. From the combination of those two, we have got these two things, the BCM and the omega. And now we just need to apply the formula for kinetic energy to calculate the total kinetic energy of this body. So the sphere will start moving on the horizontal surface such that its center of mass is moving horizontally with the velocity of BCM, which we calculated. And while that is happening, it's also spinning about its center of mass with a clockwise angular velocity according to the omega that we have calculated below. Okay, so let's also calculate the value of omega. Okay. So the angular was 0. The linear impulse was 0.1. Okay. Mass was half a kg, 0.5, and the radius was 20 centimeters, I think. 0.2 meters. So that's 1.25 radians per second clockwise. And now the kinetic energy of this moving body is just going to be the sum of translational plus rotational kinetic energy. So So whatever this finally comes out to be, this is in joules. Okay, so hope this question is fully clear, people.
Yes, sir.
Okay, so now we move to the sort of last portion of rotational mechanics, which is a specific type of motion called rolling. So rolling in general is defined as the motion of a round object like a cylinder or sphere, such that it is in combination of translation and rotation. So let's look at an example. So something like the previous question, how that body was moving, how that sphere was moving, is an example of rolling. But also there is the whole thing of rolling in this condition when there is no slipping. So when we talk about rolling such that the body is not slipping, it's rolling without slipping on the surface, then it's a bit more specific than what we saw in the previous example. So I'll come to that also. But this is an example of an object which is rolling on a horizontal surface. So the center of mass will have a velocity which is parallel to the surface on which it is moving. So in this case, it will have to be a horizontal velocity. The center of mass will have to have a near velocity which is parallel to the ground over here, and about it there has to be an angular velocity. So VCM is horizontal and omega is the angular velocity about an axis through the center of mass. And in this case, it's again a horizontal axis. It's clockwise in this case. So this is an example of rolling on a horizontal surface. Another example of rolling could be rolling down an inclined plane. In that case, the velocity of the center of mass will not be horizontal, but it will be parallel to the inclined plane. So in this case, the VCM, if it is rolling down the inclined plane, it will be in the direction down the inclined plane, but parallel to the inclined plane itself. So you can see that VCM is parallel to the inclined plane. Now, before you write all this down, the most important thing, an object is said to be rolling without slipping if the combination of VCM and omega is such that the point of contact with the surface does not slip on it. Shall I explain this with an example and the numerical equation for this condition of no slipping also. But whenever you talk about rolling, actually the context of rolling is this case where the object is rolling without slipping. So without slipping means that the point of contact between the object which is rolling and the surface on which it is rolling, that point of contact should not be slipping on that surface. So just make a note of this definition and these two examples first, then we'll discuss more about the condition of no slipping.
Sir, 1 minute, last two words.
Wait, what happened?
Sir, last two line. Done, sir.
Okay. So now let us understand the whole concept of rolling without slipping.
Sir, I was writing actually that. Done, sir.
The no slipping condition for rolling. Let's understand this. So let's start with the example of an object rolling on a horizontal surface. So the center of mass of this object has a linear velocity we are representing by this vector, let's say. This is the center of mass and this is the velocity of the center of mass. While at the same time it's spinning like this about the center of mass. Okay. Then the point of contact with the ground, which is this point P over here, the condition for no slipping is that the instantaneous velocity of the point of contact should be 0. Now you might ask, how is that possible if the object is moving, some point in it is having 0 velocity? So for that, I'll just remind you the general concept that if an object is moving such that the center of mass has a velocity omega like v like this, and about the center of mass there's an angular velocity omega, and we're talking about any general point like this, let's say, then if that point has a position vector r with respect to the center of mass, then we know that the velocity of the point with respect to the center of mass is omega cross r, because relative to the center of mass, the point P is in circular motion. Such that its radius vector is r and the angular velocity is omega. So then based on this, now we can say that the velocity of the point P, therefore, in the ground frame will become the velocity of the point with respect to center of mass plus the velocity of the center of mass. So the general formula for velocity of that point becomes omega cross r plus vc. This is something from kinematics of rotational motion which you have seen before. So now, for example, if you look at this particular body, you'll understand that suppose this was only spinning about the center of mass. If it was in pure rotation like this, then what would be the velocity of this point P? It would have been backwards like this. the velocity of that point P would have become r omega, because the radius of this is r. Like this, okay. So you would have seen here that the velocity of the point P would have just been omega cross r, which would have come out to be like this. So the magnitude would have become r omega, and the direction backwards in this particular case, if it was only rotating. Similarly, if it was only translating, there was no rotation and there was only translation. So the center of mass is only moving, there is no rotation about the center of mass. If that case were taking place, then it would be a case of pure translation. So every point would have the same velocity as the center of mass. Okay. So then this point P would also have a velocity like this. This was only translating or in pure translation. So now, as both the things are happening simultaneously, which you can see in the diagram on this side, the net velocity of the point P, you can see, is VCM in the forward direction minus r omega in the backward direction, and that should be 0. So the condition for rolling is that the angular velocity and the linear velocity are related by this constraint relation. Okay, so this is a constraint relation between the linear velocity of the center of mass and omega about the center of mass, so that the point of contact does not slip.
Sir,
Yes.
sir, how that VP vector should be 0? What? Not
How that?
VP vector
Ah,
is 0.
what? That only I've explained here. Na? If it was only rotating, then it would have a r omega velocity towards the left. If it was only translating, it would have a VCM velocity towards the right. So when both of them are happening together, what is the net velocity? It's VCM minus r omega. Na?
Okay.
So that is the condition for it to be at rest or not slipping. Okay, so make a note of this constraint relation for no slipping. Okay, so another aspect, another interesting aspect of an object in rolling condition, you see.
Sir, 1 minute.
Okay.
Done, sir.
Okay. Okay, now few more aspects about the kinematics of rolling. And as I said, rolling generally means rolling without slipping. So the moment we have that condition that V is VCM and omega are related like that, that VCM is equal to R omega, such that the point of contact instantaneous velocity is 0. We can also see that specifically if the point of contact is having 0 velocity, then so this condition, it also implies that if you take the top point, the highest point is this point A, it large velocity in comparison, because for that point it will be the sum of VCM plus R omega. Because for that one, R omega is in the same direction as VCM. So it will become 2 times VCM. Okay. Similarly, if you take this point as B, you will see that for this point, VCM is in this direction, R omega is in this direction. Okay. So for the point B, it is omega cross R plus VCM. So this omega cross R will be like a minus R omega J cap. And this VCM is like a VCM I cap. So the velocity of that point B will become like a VCM into I cap minus J cap as a vector. So the net velocity of this point B will become like this vector over here. It will have a magnitude of root 2 times VC, and this angle will be 45 degrees. Similarly, if you talk about this point here as C, for this point C, R omega is in this direction, whereas VCM is like this. So the net velocity of this point will also be like this. It will be root 2 times VCM, and this angle will also be 45. Okay. That same kind of logic. So these are few of the special points. Okay. So the 2 points on the horizontal diameter will have velocities which are of root 2 times VCM magnitude, and at 45 degrees with respect to the horizontal like this. Whereas the highest point on the object will have a velocity of 2 times the velocity of center of mass, horizontal velocity of 2 times, because the point of contact below is at rest. And the other thing is that the kinetic energy So in this, we'll apply the condition that the no slipping condition. So the kinetic energy becomes half m plus I by r square into VCM square. You can also write it as half mVCM square, which is the kinetic energy of translation, multiplied by this factor I by mr square, which is a dimensionless factor. So this factor, this is equal to, for example, it is half for a cylinder, solid cylinder. It is 2 by 5 for a solid sphere. It is 2 by 3 for a hollow sphere, etc. Okay, so finally, we will
Sir,
Sir,
look
one
at
minute.
I haven't finished writing this down.
Sir, could you also show the right side part?
Okay, so this part is clear now. So now let's look at an example where this situation of rolling is actually created because of friction on the ground. So friction prevents slipping by acting in such a way that it enables the rolling condition. So let's say this is a rough surface and this is a solid cylinder. Mass m and radius are initially at rest. Now what we do is from t equal to 0 onwards, we start pushing it horizontally. Instead of a sharp impulse this time, we start pushing it with a constant horizontal force such that the line of action of that force actually passes through the center of mass. So a constant horizontal force F starts acting. Its line of action through the center of mass such that the cylinder rolls without slipping. Okay. So given that the mass of the cylinder is, let's say, 10 kilograms, the force we are applying is, let's say, 15 newtons. The radius of the cylinder is, let's say, 2 meters. We want to find the friction acting at the point of contact, okay, the linear acceleration of the center of mass and angular acceleration about the center of mass as the rolling occurs. Okay, so let's understand here what will happen is that the weight and normal reaction are anyway acting like this. But the moment we apply this horizontal force, what happens is that the point of contact, it has a tendency to start slipping like this, because if there was no friction, then the center of mass would simply accelerate like this and there would be no alpha. So the point of contact would have slipped in the forward direction. So to prevent that slipping, what happens is friction acts backwards. Okay. And the moment friction acts backwards, you can see that friction also creates a torque about the center of mass. So there is some angular acceleration and there will be some linear acceleration of the center of mass. So as a result of this, now instead of the body going this way, under the action of these forces, the body will start moving like this, that the center of mass, after some time, it has a velocity which is acceleration into time. And about the center of mass, there is an angular velocity which is alpha. Okay. So the first thing is for the no slipping condition, that is VCM should be equal to R omega. Now VCM is acceleration of the center of mass into time. Omega is angular acceleration into time. So we get a new constraint relation that acceleration of the center of mass should again be radius into alpha. So this becomes our first equation over here. It becomes the constraint for no slipping condition. But this time the constraint is between acceleration of the center of mass and alpha. And the next thing is translation. Net force is equal to mass into acceleration of center of mass. So here that will tell us that capital F minus friction is equal to MAC. Obviously, normal reaction is balancing energy, so we don't have to worry about the vertical direction. And the third equation is the rotation equation, that net torque is equal to I alpha about center of mass. Now, as far as net torque is concerned, you can see only friction is providing torque. All of the other forces are acting through the center of mass. So your net torque is going to be torque due to friction. Which is a clockwise torque, you can see. So that should be equal to, it was a cylinder, so mr square by 2 alpha. Alpha is also clockwise. So this is my third equation. Now we have the three unknown quantities. The friction is unknown, alpha is unknown, ACM is unknown. And we have the three equations. So we're going to solve these equations. So just make a note up to this point, then we'll discuss the solving of the equations. Okay, so let's look at the final equation solving part now. So to solve these equations, what we do is in the third equation that we've written, we substitute alpha as A by R. And then we can cancel off 1 R here and 1 R here. So this equation becomes, okay, and now we substitute this in equation 2. So you can see that capital F minus MACM by 2 is equal to MACM. So that tells us that F is equal to 1 plus half. So the acceleration of the center of mass becomes 2/3 of F by M instead of F by M, because the friction comes into action. From that, you will see that alpha will become 2/3 F by MR. And from that, you will see that the amount of friction acting will be F by 3, capital F by 3. So that answers all three parts of the question. Okay. You can substitute the values numerically and get the answers in SI units. But the important thing is understanding the no slipping constraint relation, that if VCM is equal to R omega, that means A has to be equal to R alpha. Acceleration of the center of mass has to have the same relationship with alpha as VCM has with omega. And to facilitate that, or to create that situation, how much friction is required? This is the amount of friction required. Okay, so tomorrow I believe we have one more class in the afternoon. So we'll continue from this point onwards. Okay. So please make sure you go through these last 2 or 3 examples and the whole definition of rolling and no slipping condition and all this very carefully. Because tomorrow we'll be doing plenty of problems, more numerical problems based on this. Okay. And with that, we'll complete rotational mechanics. So that's it for today's session. Yes, Bhargav,
Thank
you have
you,
a question?
sir. Why, sir?
No, sir, nothing.
Okay, okay. So that's
Thank
it for
you, sir.
today. Yeah, sure.